So, hello everyone, I'm Dominik, and this is kind of like a continuation of what Thierry has done and basically using his data to do experimental design for seismic mass movement monitoring. And we do experimental design here because we have this amazing data set over here, and you've seen the landslide just now. And since there are like 1,000 stations, this means we can basically do experimental design, then pick out our designs and really use actual data to kind of benchmark and analyze how good those designs perform in practice, to kind of see what choices are important and what are not. And I want to start with a brief introduction about experimental design. This is going to be quite schematic, so if you want to have any more theoretical explanation, come and talk to me afterwards. So typically what we have in Bayesian problems, and we are taking a Bayesian experimental design approach here, is some form of prior information. And what you can see here is basically a prior that builds upon this surface displacement that you've seen before. So here we just assume that seismicity is proportional to the surface displacement, and this is where we expect seismicity to occur. Then we can have a little exemplary design made out of 4 stations, and then we can have a synthetic event here and do the whole Bayesian posterior inversion here, which is this red blob that you can see here. So the redder the red contour, the more likely we think the event has occurred in a certain area. And here you can see we resolve the true event quite accurately. But of course we don't know where the true event occurs, so we can do this process for a number of different true events and have a look how the posterior looks. And we always want to have this posterior distribution to be as concentrated as possible. And we can do this for a number of different events. And now to compare to another design, I will just put all of those posteriors into one big picture, but each of those is for a separate event. But it's just for comparison, so you get a visual feeling. So how about we look at a different design where the stations are kind of evenly distributed, but slightly different than before. So now all those different posteriors are a lot more spread out. So intuitively you can just say this is a worse design because we get less information where the seismicity has actually occurred. And for those of you familiar with Bayesian statistics and information theory, here quickly the quality criterion that we used. It's the so-called expected information gain, where we average over all the data that we possibly can observe according to the prior, and then we just take the difference between the information in the posterior minus the information in the prior. For those of you not so familiar with those concepts, we just want to maximize the difference between this big blob and those small red blobs. And the smaller those red blobs are, on average, the better our design is. This is kind of the intuitive explanation of what we have here in a formula. So what do we need to do an experimental design? I will briefly go over all the inputs that we have to choose before starting. So the first thing is, of course, our model prior. And you've seen the one on the right before. But in many cases, you might not have that information. So you could be a lot more conservative and just set a uniform prior around your area where you can place your nodes. And there you don't do any major assumptions. But of course, your design won't be as focused on where the true events occur. Another important component is the velocity model. Of course, in this case, we were lucky. We have this really nice 2D or 3D velocity model. But in many cases, you might just only have a gradient model available or an estimate of a gradient model, or you have basically no idea and you just take a homogeneous velocity model to just have any travel time data. Then, of course, the velocity model has uncertainty, the data has noise, and the noise is distributed according to some statistics. Then we have attenuation, so we won't always pick up an event, and we can describe that often only heuristically because modeling it would be very hard because we don't have the underlying information. And then, of course, some receivers have an angular sensitivity. In the simplest case, DAS can only see certain directions because it's a one-component sensor that only reacts to strain in one component. And to introduce those last 4 points, we have kind of developed a framework of how to do that. So we start with a single source location and an experimental design, which is here 5 receivers. Each of those is described by a coordinate in 3 dimensions. And then we can use the design and the source location to put them into a travel time simulator. There's also where our velocity model and topography model come into place. Then we can predict travel times for each of those stations. And now the kind of new part that has not really done before is that we have a so-called, what we call picking likelihood and a random source strength parameter. And this picking likelihood now gives us where do we actually observe a travel time. So here we just generate a mask and 3 travel times go through. And for 2 stations, we obviously know the synthetic travel time, but we say we have not observed it due to that mask. And I will briefly go into how we can generate this mask. So what you can see here is data that Tjeerd has picked painfully by hand. And you can see here the offset versus the travel time. And this is now for the whole landslide body. And here the interesting part is in the histograms. In blue you can see where a travel time has been picked. And in red that shows you where we know we have a dynamite shot and a offset, but Tjeerd could not find a travel time. So this means because of some reason, probably attenuation or noise, we don't have a travel time pick. And when we look at the other marginal, we can see that after a travel time of 0.35, we have this very steep decline in travel times that we can actually pick. So basically the mask that we use here in the simplest case is just using this picking probability, which means that below 0.3 seconds, all the travel times are picked, and above 0.5, nothing is picked anymore, and in between it's kind of a bit of random. So we take into account that sometimes we can still pick in this area. And then we use this so-called the masked travel time to set this as a mean of our data likelihood, which in this case is just a Gaussian or a normal distribution. But of course we also need to define how the covariance for this data likelihood looks like. And the simplest component would just be to use the picking uncertainty, which is set to 0.01 seconds for all the stations, put that through this kind of adapted picking mask, and have our 3x3 covariance matrix. But there are a number of other noise statistics that we might want to model. So for example, we can use our receivers and calculate this interstation distances, because you might assume that close stations have correlated noise. So what we can do then, use those distances to calculate a correlation matrix, and then together with an estimate of the velocity model uncertainty, have a sort of correlated idea of how the velocity model uncertainty affects the data we observe, because especially for velocity model uncertainty, similar ray paths will of course have a similar uncertainty if we don't know the velocity model quite well. So this is kind of a number of ideas how to model all those different noise statistics. And then of course, this expected information gain I introduced before is quite difficult to calculate in practice. So there's a number of different algorithms that we could use, and some are more accurate, a bit more expensive. Some have different assumptions but are computationally cheaper. And I just briefly want to mention the Laplace method here, which assumes that the posterior is a Gaussian, which is quite a severe assumption, but it's very easy to use that method to introduce that whole picking likelihood and masking of travel times. But we will compare all 3 of those methods. And of course we need an optimization algorithm to actually find our best design. And here we use a very simple one, which is called sequential construction, where we first look for the best position for our first receiver, then take that as a given, and given that first receiver, look for the best position of the second receiver, take those 2 as a given, look for the best for the third, and so on until we have the network that we really want. And in total, we generated around 150 different designs with a wide variety of different input parameters, and we benchmarked them with different methods. So, well, since this expected information gain is a very unintuitive quality and it doesn't really say much, even if you work with it on a daily basis, the value we use here for benchmarking is an average mean distance over the first 15 iteratively placed receivers. And I will quickly go bit by bit what I actually mean by that. So assuming you have those 2 receivers and that is your posterior. So the mean distance now is, for every point in a grid here, we look how far is this point away from our true event, which is the star. And then we weight this by the probability that the event has occurred there, which is just the red, or how red this place is. So everything down here we would just not take into consideration at all because it's very unlikely to happen. But for example, those areas would still make the mean higher because those are quite far away, but still likely according to the posterior. And then we do this for a number of different events. And then we average the whole thing over the first 15 iteratively placed receivers. So you can see here, the more receivers we add, the smaller our uncertainty gets. And for each of those networks, we take a number of true events, calculate this mean, and then average it over all the different network sizes. So this is kind of a one number to describe how well certain design inputs are performing. So the first benchmark I want to show is on the shoulder of the landslide. And here we really have this unique opportunity to select our designs and really use actual real data to benchmark our designs. And here we generate optimum designs, assuming that seismicity occurs only on the surface and only where we have dynamite shots. So this is kind of a 2D source location problem, but we still take the full 3D physics into account. And what you can see here now is that here we can analyze how good different velocity models as input parameters perform. And each of those axes is a different setting. The only thing equal between them is the velocity model. And here you can see that, as we would expect, the better we know our velocity model, the better the designs are performing. And you can also roughly see in meters how much better or worse they are performing. But you can also see that, for example, a gradient model, which is often reasonably to assume, or we can get a reasonable estimate of that one, performs very well compared to having a full 3D velocity model, which is hard to get in practice. And some of you might be interested how those designs actually look. So this is the best performing design at 5 receivers, so you kind of see a bit of a structure. And here, the worst performing at the stage of 5 receivers. And at least I could not decide which of those two designs is better. They're both kind of evenly distributed. And you can see here that the distance, the mean distance can get quite large. Also, the trade-off between those designs is quite big. And here we can again do the same thing and have a look at how different methods perform. The only really thing I want to show here is that luckily for us, the cheapest method performs actually the best. And that for the small area, it doesn't really matter if we include attenuation or not, because we kind of have to use a worse method to introduce that attenuation. So in this small shoulder area, it doesn't matter too much. But of course, we can also use the full data set. Now we don't have the luxury of having those dynamite shots everywhere. So now we do the experimental design for the best design on everywhere. And the data we compare to is now synthetic, which is still quite good because we have a very good estimate of the true velocity model, which we typically also don't have. So this is also still a great benchmark, I think. And we can again generate those comparisons. And here, the only thing that really changes here is that we have two different priors. So one's the displacement prior, which is more focused to the top, or the uniform prior, which can be everywhere. And we assumed that the true distribution is this displacement prior. So here in the little circles, you can see all the designs that were generated using this uniform prior. And you can really see that the prior has a really big effect on how good my final design is performing. And you can also see that on this bigger scale, attenuation actually plays an effect and can even compensate for using a method that has a stronger assumption built in. So for small problems, attenuation is not as important, but as soon as we go bigger, it's quite nice that we can include it now. And here again, the worst performing design at 5 receivers and the best performing. I couldn't tell which is better. So now we switch topic a bit. So now we see what we can do with that whole setup using DAS. And the curious thing about DAS, so here you can see the sensitivity of a single DAS gauge length with a certain angle for P wave arrivals. So this is really only P wave arrivals. And you can see that this little gauge length can really only see forwards and backwards and not to the side because it's a 1D strain sensor. And then you can see that if we also include attenuation, we have this kind of sensitivity cloud in the 3 planes. And then we can use that to do this iterative construction process again. So here you can see the color indicates the best position, and the angle of those little rectangles indicates the best angle or the best gauge length direction at those positions. And here you can also see how a single gauge length sees the world. So we can place this first gauge length, then look where's the best position to place a second gauge length, with no consideration that those have to be connected or close together. And then just bit by bit build up a collection of gauge lengths. And this is of course not a full dust design, but if you go into the field, this would kind of give you important spots that you have to travel through with your dust cable, and also give you at what angle do you have to go through at this point. And we try to use some genetic antenna optimization algorithms to actually optimize a single cable design, but this turned out to be very difficult, and basically the genetic algorithm only learned to stay in the middle of the survey area, because as soon as it got a step outside, it got a huge penalty because it's not allowed to be there. So there's a lot of room for improvement to actually get a single best dust cable design. And then of course we can also do a hybrid study. So here we assume that the dust cable is given, and then have a look where do we place our first 3 best complementary node stations. Yeah, and to conclude, this really densely instrumented real-world scenario is a unique opportunity to allow us to benchmark experimental design algorithms and choices. And by incorporating this picking likelihood, allows us to include receiver angular sensitivity and to give design recommendations for dust algorithms. And really the outlook now is to really summarize that very concisely and give recommendations for future deployments, and really tell people what is important, where can you neglect stuff. For example, we found that noise correlation seems to be really unimportant in this case for some reason. So that's kind of the idea, to really give recommendations for future deployments. And all the algorithms are openly available. Thanks for your attention.